Good morning, all. So, I was asked in the seminars this morning to go back over action potentials. I'm going to basically show you this animation, talk you through it, and hopefully that'll make it life easier for those people who are struggling. So, first things first, we have to understand that in order for an impulse to travel along a neuron, you have to have an imbalance of ions, an imbalance of ions, and that has to change in order to change the membrane potential. So, we have to in some way move the potassium and sodium ions around. So, when we're at rest, what we're looking at is a negatively charged inside relative to the outside. And what's happening here is that potassium ions are being pumped in, and sodium ions are being pumped out of the cell, and that potassium ions are therefore going to be at a high concentration inside. They are then able to diffuse out of the cell via their leak channels. But sodium ions can't get in. So the idea, sodium ions being pumped outside, potassium pumped inside, and then potassium ions will then diffuse out of their leak channels and into the surrounding tissue fluid. And so overall, most of the potassium ions and pretty much all of the sodium ions end up outside. And that's what causes this negative membrane potential, which is fine. This animation symbol I've just noticed had the potassium ions diffusing in. Somebody's mismanaged that. They should be diffusing out, most definitely. And you have this resting potential of about minus 70 millivolts. I don't think that's the bit most people are struggling with. So, when you have a stimulus, what's going to be happening is that the membrane permeability for sodium ions is going to change. And broadly, when you have a stimulus, this sodium ion gate is going to open. And because of that, what will happen is the sodium ions will diffuse into the axon. Now, make sure you understand the inside is orange, the outside is purple. So I said earlier, there's a lot of sodium ions outside, and when this sodium gate opens, by diffusion, they move in. Now this will open because of change in the local membrane potential next door. That can either be because prior to this, on the next section of membrane, the same thing has happened. So sodium ions have moved in next door, and that slightly changes the membrane potential here. It can be because of a receptor activating, which we'll learn about later in the course, or it can be because of a neurotransmitter attaching on here and opening a sodium ion gate. Either way, a sodium ion channel has to be opened. Sodium ions rush in. And that's the first stage. Sodium ion channels open because the local membrane potential changes, and that allows sodium ions to rush in. And that is called depolarization. Because these sodium ions rush in, we go from about minus 70 to about plus 40, because we suddenly have a lot of positive charge inside the cell. Now, what will happen next is that once you get to plus 40, the sodium ion channels inactivate and potassium ion channels open. That allows potassium to leave the cell much faster than it otherwise would. Let's call that a little bit fast. Because the potassium ions leave, that will mean that, as well as that, the sodium ions are being pumped out, as they do. And so overall, a lot of the potassium ions will end up outside. All of the sodium ions will end up outside as we repump everything back out. And so you will end up with, again, minus 70, because the potassium is able to escape and sodium is not able to get in again after it's pumped out. This is all down to, once we get to the top of the membrane potential, plus 40, this potassium gate opens, allowing potassium to leave much faster. Now, this causes a wave of depolarization, and broadly, the flow of sodium ions moves ahead of the action potential, which means the next section will also open. So depolarizing the previous bit causes the next bit to happen. It's almost like a Mexican wave. Activating one thing will also activate the next thing. Now in this case, you've got the action potential being the purple bit, and the sodium ions entering being the red bit, because the sodium ions spread out. Fine. Now, This is going to be about synapses. I will touch on this very briefly. I'm going to make sure that everyone understands this. If you've got synapses, you can kind of leave the video there. So we've got this idea here of this being the presynaptic neuron, this being the postsynaptic neuron. Now, as we get depolarization arriving because of this previous sodium ions moving in, that opens calcium channels. Calcium ions then flood in because we maintain a high diffusion gradient with all the calcium ions outside. When those calcium ions move in, they cause these vesicles here to move towards and fuse with the membrane, which means all of these neurotransmitters end up on the outside here. These neurotransmitters will be in the synaptic cleft. They will then diffuse across fairly slowly for a nervous system thing. So this is what takes the time, is the diffusion of these chemicals. They then activate these receptors. When these receptors activate, what's going to happen is that it opens sodium ion channels, and this is a key point people don't realize, is that when these attach here, what's happening is then we've opened some sodium ion channels on the postsynaptic membrane, allowing sodium ions to flood in, which then starts this all over again, because the sodium ions flooding in here will depolarize the surrounding sections and cause their sodium ion channels to open as well. Now, we're either going to actively transport the neurotransmitters back in, or if it's acetylcholine, we're going to break it down and then reabsorb it by diffusion. Fine. If you're struggling with any of that, hopefully this has been helpful. Otherwise, scroll back and find the bit which you're stuck on and just watch it a few times. If you're still stuck, then obviously ask me. Hopefully that's been helpful. Have a good day.